Hello everyone, Techie Dheeraj here. So this video is about the Amrita CTF qualifier round. So I have solved many challenges in that CTF. So I am going to write, give some write-ups for them. So this write-up is about the bind exploitation category, which comes under pawn, and challenge name is HellCode, and the point for that challenge was 300. This is the description for that challenge, and this is the server address where that binary was running. Okay, so let's jump into the binary. So this is the binary we have. So as we can see from file, this is the 64-bit executable, and it's a not stripped, and it's a dynamically linked binary. So before jumping into GDB, let's open a decompiler for this. So I use a Ghidra for this. So I have loaded this binary. We just have to open it and analyze this. So let's make it open. So yeah, it's loaded. So we have to just analyze it, and once it's analyzed, we can see the main function. Like as we can see the main, so this is the decompiled code of main. So as we can see here, this is the array of 32 bytes. It's declared, and there are some it's asking for shell code, and then there is a getters for the buffer, and buffer is stored in basically a data segment. So it's a global array, globally declared array, and it's using mprotect. So mprotect is nothing but with the help of mprotect we can change the permission of that particular segment. So from like if you want to make a stack executable, so we can give the particular addresses, and we can change the permission of that particular area, memory area. So that's what it's been doing here. So it's changing the permission from global offset table address up to the 1000 bytes. This is the size, how many till how many address you want to change the permission, and 7 basically is a uh, uh, basically octal number, we can say triple one. So this is a read write and executable permission. So it's changing a stack permission for that. So and asking here for the again getters. So from seeing this, what we can do is what we have to do is basically uh, it's asking for shell code here. Shell code, if we give the shell code, then we can get the if we jump to that address, we can get the shell. Okay, so what we have to do, we have to get a shell code, and we have to write a shell code in this buffer. Okay, and we have to first clarify whether this buffer comes under this address or not, because if it doesn't, then we won't be able to execute this shell code. To execute this shell code, that particular memory area has to be executable. Okay, so we have to verify this whether this buffer comes under this address or not. And after that, with this help of getters 32 bytes, we can change the return address of this main. So when we can overflow this buffer, and if we change the return address of this uh, return address of this main, then when this main is going to return, it will jump directly to that particular memory area where this shell code was written. Okay, so this is the overview of what we have to do in this. So let's jump into the GDB. So GDB. So if I just run this, so this is the buffer. As we can see here, this is the set vbuff, and here it's a printing to the two printfs which we saw. So here hello there and give me shell code, and it's loading the effective address of the buffer here in this RDI, and then it's getting the getters for the buffer. Okay, so and here it's calling the mprotect. Okay, so what we have to do is we have to first identify the address of the buffer. Okay, that is a one thing we have to do. Okay, so apart from this, okay, so we have to do we have to see the addresses, like this is the address. Okay, and we have to run the nm first, because through the help of nm we will be able to find out which is the starting address where the m protect is working. As we can see here, global offset table, this is the global offset table, is changing the permissions, so it's 1000 bytes, and it's writing to read write and executable. So we found this address through here, 404,000. So this is the starting address, and up to 1000 bytes it's changing the address. Okay, so as we can see here, this is the address here. So this is the 1000 bytes is adding from here. So this is not the 1000 byte, this is a 4 KB page, we can say, because this is in a hex, so it will be, the difference will be 4096, which is a 4 KB, 4 kilobytes. Okay, so I will show you, because this is a process ID, so we can see maps of this process ID. So if we see here, so this is the address which we were talking about earlier. So here only read write permissions are there. So executable is not there. So this memory area is not yet executable. So it will be executable after the m protect. Okay, so let's just let me uh, explain you guys how this memory area is getting memory area permissions getting changed. So if I add breakpoint, or if I jump to that breakpoint, if I again run this, then you will be able to see the executable permission is there. So mprotect is changing the permission of this area. So let me just get one shell code. I have one written here. So this is a shell code. So I have to write. So let me just explain where that buffer is. So buffer is starting from here. We can see here in the set v buff is a passed, after the set v buff there is a buff, so it's getting loaded here. After the put s, so this is the put s. If we see here, so if we print this area, you will see this, the string. Okay, so okay, so these are the strings, because it's a overwritten, right? Because the instruction pointer will change, so that's why we are not able to see the proper. But if we add, if we check at this breakpoint, you will be able to see the exact string. Okay, if we check it here, okay, so let's jump to the main point where this buffer is declared. So this is the buffer. So this is the buffer address. So as we can see here, this is the buffer address. If I'm printing it here, so it's a buffer address. If I just go back some bytes, so this is, you can see this is a glibc address, and after that there is a buffer address. This is declared in the global variable, so this is from buffer is starting. So what we can do here, we have to write shellcode here through the help of first getters, which is here, and if in the second getters we have to change the return address to this buffer address. Okay, so let's just write the shell code which we have. Okay, so let's just light exploit for this. Okay, so this is the shell code I'm writing. Okay, after this, if I if we see this correctly, so as we so here this is the buffer address. So what we have to do is after this, and one more thing, because we know getters reads till the new line. So if we are passing from the input before running the program, if you are passing as an input, so we have to provide the new line character. So the new line character is basically 0a. Okay, this is a new line character. So we have to pass this. After this, if we see the code correctly, so the 32 byte array is there, and after that there will be RBP. So we have to overflow that to reach to the return address. Okay, so we have to overflow that. So the in the 64-bit architecture, all the registers are 8 bytes. So we have to overflow this, and after this we can write our this buffer address. Okay, so how we'll write? We will just give this. So this way is the return address is passed here, but we have to reverse it because we have to store it as it is. If you want to, if you if this will be stored in memory, this 70 will be stored in the LSB side because this is a hexadecimal. That's how it will be stored. So, but we want to write uh, like this, so we have to revert this. Okay, so what we can do, we can use this one to revert it. Okay, so this is the return address. So after this we have to nullify the rest of the bits of this. So how we can do that? So uh, we can just do this, and there are 5 bytes left, so we can just pass the 5. Okay, so as we can see here, so this is the 3 bytes, and this will be the 5 bytes, and the full of the 8 byte register will be occupied. Okay, so let's pass this into one file. Now let's load it. Okay, yeah, as you can see here, and this process is executing new program bin dash. So why it's showing bin dash? Because I am executing shell code of sh shell, which is a symbolic link to the bin dash. If even if so that's why it started executing, which means it's our shell code is working. Okay, so to clarify a little bit more, what I can do, so we need to delete this point. Okay, so I want to just clarify. Okay, so if I just it again. Okay, actually because the shell ran, and that's why it's showing some errors in this. That's why it's not able to, because if you see here, it's starting the shell again. So we will just load this again. So let's just disassemble this. So I will just add a breakpoint here. I just want to show the, because we reached here, if I do this instruction pointer, you see RBP is overloaded with this address with this, instead of address with this 14 1, which is a hexadecimal uh, value. And if I check the RIP register, so this is the RIP register here, if you see. So if I just step in here, you can see I am inside this buffer. So if I jump again to the RIP, if you can see we are inside the buffer, so it means our buffer is overflowed and we are into that exact stage. And if I dump this memory here, you can see we have that shellcode. We are at the stage where shellcode is written, so it will be executed. So now how we will check it? So we will exit this GDB and we have this input, and in the here we have the server address. So we just have to get this input and pass this to the server, and it should return us a shell. Okay, so as if I do ls, you can see it's returned us a shell. So it's a perfectly whole for this was the flag which we needed to give. So this is all for this challenge. Thank you all.